Good day to Dr. Wong. My name is Zidhiski Hazimin and my matrix number is J25A1684. Today I am delighted to present my video assignment for the Organic Chemistry course. This assignment covers some of the most fundamental and fascinating concepts in the field, which are essential building blocks for understanding chemical synthesis. As you can see on the slide, this presentation will focus on four key areas. Organic reactions, we'll be looking at the basic mechanism, how and why molecules change. Alkenes and alkynes, we will explore the characteristics and reactivity of these crucial unsaturated hydrocarbons, paying close attention to the double and triple bonds. And stereochemistry. This is arguably the most complex and interesting part. We will discuss how the 3D arrangement of atoms influence molecule properties and reaction. Think of it as molecule shape and handedness. The goal of this assignment is to synthesize all of these concepts to show a comprehensive understanding of how carbon-based molecules behave. I hope this video provides a clear and insightful discussion on the material. Without further ado, let's begin our deep dive into the world of organic chemistry, starting a closer look at the different types of organic reaction. Now, let's move into section 1, types of organic reaction, the foundation of this course. Organic chemistry involves countless transformations, but nearly all of them fall into three main categories. Addition reaction, which is joining molecules. First, we have addition reactions, which are all about joining molecules. The concept is simple. Two or more molecules combine to form a single, larger product. This usually happens when we react a molecule with a double or triple bond, like alkene or alkyne, with another region. We break that weak multiple bond and add new atoms across it, making the molecule more saturated. The second one, substitution reaction, the swap. The key concept here is that one atom or group of atoms in a molecule is swapped for another atom or group. Think of it as a direct replacement. One group leaves and a new group takes its place. The overall structure and number of bonds in the main molecule usually remain the same. And the last one, which is elimination reaction, the removal. Finally, about this, the concept is that the two atoms or groups are removed from a single molecule to form two products, often resulting in the creation of a small byproduct like water. This is essential, the reverse of an addition reaction. By removing atoms, we create a new double or triple bond, making the product less saturated than the starting material. These three reactions, addition, substitution, and elimination, are the core language of organic chemistry. To better summarize these concepts, let's look at each reaction fundamentally. Changes the starting molecule in terms of the number of groups attached to and its level of saturation. Addition versus elimination. Starting with addition reactions on the left, they increase the number of atoms or groups attached to a molecule, reducing the unsaturation. We go from a multiple bond to all single bonds. On the opposite side, the elimination reaction are the reverse. They decrease the number of atoms or groups attached to a molecule, increasing the unsaturation by forming a new double or triple bond. And finally, in the middle, substitution. These are the most neutral, chemically speaking. They simply replace one atom or group with another, maintaining the saturation level. Nothing is gained or lost overall. It's a simple equal trade. Understanding these differences, how attachment and saturation are affected, is key to predicting the outcomes of any organic reaction. Now let's bring these concepts to life by looking at our three example reactions on screen. Focus on the top reaction, which is elimination. We start with a saturated single bonded molecule and end up with a double bond. Since we remove two atoms, two hydrogen, to create that double bond, this is an elimination reaction. The middle reaction, substitution, observe the change at the rightmost carbon. The original OH group has been directly swapped or substitution for the bromine atom, with no change in the molecule overall saturation. This is a substitution reaction. And finally, at the bottom reaction, addition, we start with a double bond and add two hydrogen atoms across it to form a single bond product. By joining molecules and increasing saturation, this is clearly an addition reaction. Now, for real-world example, these reaction types are the chemical foundation for things we use every day. Addition reactions are critical in polymerization, the process used to manufacture most plastics, like for bags and bottles. Substitution reactions are widely used in pharmaceutical drug synthesis. And lastly, elimination reactions are key in the industrial dehydration of alcohol. Let's finish this section by making a complex topic simple. How to name alkenes using IUPAC rules. Alkenes are just molecules that can have a special feature, which is a double bond. Number 1. Identify and name the main chain. The first step is to find the longest chains of carbon atoms that include the double bond. That chain sets your base name. To show it's an alkene, we take the usual ending, which is at the back at ANE and change it to ENE. For example, a 5-carbon chain becomes pentane. Number 2. Locate the double bond. Second, we have to say where the double bond is. We number the chain starting from the end that gives the double bond the lowest number possible. We only use the number of the first carbon in the bond. So if the bond starts at carbon 2, the name is pen2ene. Finally, we add the details. We use the established number to name any side groups, like methyl, and list them at the beginning. And because of the double bond can't spin, we sometimes need to add cis or trans at the start to indicate its exact 3D shape. That's it. Find the chain, change the suffix to ene, number the double bond, and list the branches. This gives every unique alkane its own clear name. Since alkenes are so important, let's look at the two basic laboratory methods used to prepare them, both relying on the elimination reaction. The first method is dehydration of alcohols. Dehydration simply means removing water. We take an alcohol like ethanol and heat it with a strong acid catalyst, such as sulfuric acid. The acid helps to remove a molecule of water from the alcohol. As shown here, the elimination of H and OH from ejection carbons create a double bond, giving us ethene. The dehalogenation of alkane halides, it means removing a hydrogen and a halogen. We react an alkene halide like bromothane with a strong base such as potassium hydroxide under heat. This process eliminates hydrogen halide from the molecule. In both cases, the key takeaway is that we eliminate two groups from ejection carbons from the new double bond. So these two are key reactions of alkenes. The first one is hydration, adding water. Basically, you add a water molecule across the double bond. And the second one is hydrogenation, which is adding halogens, where you add a halogen molecule across the double bond. Now, for real-life use, the most obvious one is polymerization, which are plastic bags. So the nomenclature of alkenes are named by selecting the longest carbon chain containing the triple bond, changing the suffix to YNE, and numbering the chain to give the triple bond the lowest possible number, while also locating any substituent groups. For the method of preparation, alkanes are commonly prepared by the double dehydrohalogenation of vicinal or chemical dehalides using a strong base. It starts with an alkene and adds a halogen, bromine or chlorine, to form a vicinal dehalide. Here are two reactions of alkenes. For application, we mainly use this for welding. This powerful heat is essential for melting and fusing metal in construction and manufacturing. Finally, we come to the last section of our assignment, stereochemistry. This concept deals with how the 3D arrangement of atoms affect a molecule's properties. Constitutional isomers are molecules that share the same molecular formula but have different connectivity. They are built with different Lego instructions. In contrast, stereoisomers are molecules that share the same molecular formula and the same connectivity, but differ only in the spatial arrangement of the atoms. They are just different 3D shapes of the same structure. Chivalry refers to the property of a molecule that is non-superimposable on its mirror image. A chiral molecule lacks an internal plane of symmetry. The most common cause of chirality is a carbon atom bonded to 4 different substituents, which is called a chiral center or stereocenter. For a real-life example, my hands are chiral. My left hand and right hand are mirror image to each other, but they cannot be superimposed perfectly. Enantiomers are a pair of molecules that are mirror image of each other, but are non-superimposable. Enantiomers have identical physical properties such as melting point, boiling point, and density, except for how they interact with plane polarized light. For example, real-life example is thalidomide had 2 enantiomers, one of which was effective against morning sickness, while the other caused birth defects. Optical activity is the ability of a chiral molecule to rotate the plane of plane polarized light. When plane polarized light passes through a solution containing a chiral compound, the plane of the light is rotated. Enantiomers rotate plane polarized light in an equal but opposite direction. If a compound rotates the light clockwise, it is designated as dextrorotatory plus. If it rotates the light counterclockwise, it is designated as levorotatory negative. For a real-life example, lactic acid has 2 enantiomers. One enantiomer will rotate plane polarized light clockwise, while the other rotate it counterclockwise. To explain it briefly, diastereomers are non-mirror image, non-superimposable stereomers. Meso compounds contain chiral centers but are achiral due to internal symmetry. Grace mixtures are equimolar mixtures of enantiomers and are optically inactive. So these are the reference I used during the slide, and that's all for me. Thank you.